All right, today we're going to look at section 9.1 on mathematical patterns. We are starting a chapter that deals with sequences and series, and our focus today is just understanding some of the terminology, looking at how do we write recursive and explicit formulas, and finding terms of a sequence. So in general, a sequence is just an ordered list of numbers, and the terms of a sequence are each of the numbers that you see in the sequence. We use little subscripts to represent the position of the term. So for example, a with a little subscript of 5 represents the 5th term of our sequence. So in our example here, we have our first term, a sub 1, a sub 2 is our second term, a sub 3 is the third term, and we would keep continuing that pattern. A couple things that you're going to encounter as we go through here. The nth term, that is a generic term in your sequence, all right? The term in front of it would be the one n value smaller. So for example, if this is the 7th term, then one smaller would be the 6th term. So this little expression a sub n minus 1 just stands for the previous term. In other words, the one that is in front of the nth term. All right, so there's two ways to represent the formulas for a sequence. The first way is called an explicit formula, and it describes the nth term of a sequence using the actual number n. So it is based on its position in the sequence, not on any of the numbers that come before it, just on what position it's in. You can find the nth term from an explicit formula simply by plugging in your n value into your equation. So our example says a sequence has an explicit formula, a sub n, the nth term, is equal to 3 times n minus 2. What are the first 5 terms of the sequence? So we want to find a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. So in the first one, a sub 1, our n value is 1. So we're just plugging in 3 times 1 minus 2. 3 times 1 is 3, minus 2 gets us a 1. A sub 2, we're now going to plug a 2 in for n. So 3 times 2 would be 6, minus 2 would be 4. Third term would be 3 times 3 minus 2. So 9 minus 2 would be 7. Our fourth term would be 3 times 4 minus 2. 12 minus 2 would be 10. And our last one would be 3 times 5 minus 2. 15 minus 2 would be 13. So the first 5 terms of my sequence would be 1, 4, 7, 10, and 13. All right, our next example says a sequence has an explicit formula a sub n equals 12 times n plus 3. What is the 12th term of a sequence? So what's nice about an explicit formula is if we want to find the 12th number, all we have to do is plug a 12 in for n. So 12 times 12 plus 3. 12 times 12 would be 144, add the 3, and we know that our 12th term is 147. We do not have to find all the terms that come before it. So how do we write an explicit formula? If we're given a sequence of numbers and we're asked to come up with an explicit formula, we have to compare the number to its position in the sequence, to its n value. And you're going to be looking for basic operations like adding, subtracting, multiplying, dividing, squaring, that type of thing. Okay, so what I want you to do is start out writing your n value and then write in the number that's in that position. So my first term, the number in that first position is a 2. My second term is a 4. My third term is a 6. My fourth term is an 8. And my fifth term is a 10. So I want to look at what am I doing to n to turn it into a sub n. So what do I do to a 1 to make it become a 2? What do I do to a 2 to make it become a 4? What do I do to 3 to make it become a 6? We're looking for a pattern. So in this case, the pattern is that we're just multiplying by 2. 4 times 2 will get me an 8. 5 times 2 will get me a 10. So we just want to show that we're multiplying by 2. So I would say my nth term is just 2 times whatever the n position is. So my 20th term would be 2 times 20, or 40. Our next example says to write an explicit formula for the sequence 5, 6, 7, 8, 9. So again, we're going to start with looking at the position. So we are given 5 numbers. My first number is a 5. My second number is a 6, then 7, 8, and 9. The dot, dot, dot just means that it continues in that same pattern. So what am I doing to a 1 to turn it into a 5? Well, I could say I'm timesing by 5, but then that doesn't hold for this next pattern. Okay, so let's go back. What do I do to a 1 to turn it into a 5? My number's getting bigger and it's not through multiplication, so let's look at addition. I'm adding 4 to my 1 to turn it into a 5. Here, if I add 4 to 2, I get a 6. If I add 4 to this 3, I get a 7. Add 4 to 4 and I get 8. Add 4 to 5 and I get 9. So I'm simply taking my n value and I'm adding 4 to it. Okay, for the next one, our sequence is 0, 3, 8, 15, 24. So again, let's start with our n value. And then look at our a sub n, the numbers in those positions. Okay, now, once again, I'm going from a number like 1, 2, 3, 4, and I'm getting bigger numbers like the 5 turns into a 24. So I know that I'm not dividing and I'm not subtracting. I'm doing something that's going to make my number get bigger. If we looked at multiplication, there's no whole number that I can multiply 2 by to get a 3 and have that same thing multiply 3 to get an 8. If I'm looking at adding, to go from 1 to 0, I'm actually subtracting 1, but to go from 2 to 3, I'm adding 1. Here I'm adding 5. Here I'm adding 11, so that's not a consistent thing. And if you look at the numbers in your sequence, the 0, 3, 8, 15, 24, they are very close to our perfect squares. So 1 squared would be 1, 2 squared would be 4, 3 squared would be 9, 4 squared would be 16, and 5 squared would be 25. So to go from there to there, I'm squaring my n value. But the actual numbers in my sequence are just 1 smaller than that. So instead of 25, I'm at 24. Instead of 16, I'm at 15. So my formula says to take your n values and square them, and then just subtract 1. As we go through this chapter, we are going to be focusing on very specific types of sequences called arithmetic and geometric. So what we're looking at today is really just becoming familiar with what a sequence is and the notation that we're going to use, but it will get easier to figure out those patterns. All right, the next type. We had explicit formulas. Everything we've been doing so far has been working with an explicit formula where we are basing it on its position, its n value. In a recursive formula, we relate it to the term that's right before it in the sequence. So we don't really care about its position so much as just how are we changing the previous number to turn it into the next term in the sequence. So it relates each term to the terms before it. A sub n represents the current term. A sub n minus 1 represents the previous term. So when we write a recursive formula, there are always 2 parts. And I'd like you to highlight that. There are 2 parts to a recursive formula. There's an initial condition where you have to tell me what the first term is, or in some cases what the first couple terms are. You have to get something, give me a starting point. The second part to it is then to actually generate the recursive formula. What are we doing to the previous number to turn it into the next term in the sequence? All right, so for example, it says, what are the first 5 terms of the sequence with the recursive formula a sub 1 equals 2 and a sub n equals a sub n minus 1 plus 5? Remember that a sub n minus 1 just stands for the previous term. So if we're trying to find the nth term, then the n minus 1th term would be the number right in front of it. So our sequence is telling us that we're starting with a 2. So my first term is a 2. My second term says to take the previous number. So if I'm trying to find a sub 2, it's telling me take a sub 2 minus 1, or a sub 1, and add 5 to it. So I'm going to take my previous answer, which is a 2, and I'm going to add 5 to it. Then when I go to find my third term, I'm going to take that previous answer again and add 5 to it. My fourth term takes my previous answer, adds 5, and my fifth term takes my previous answer and adds 5. So I'm just going to continue to add 5 each time. So that's what it's telling me right here. Take the previous number and add 5 to it. Because recursive formulas use the previous term to find the next one, you must always start with the first term and work your way up to the term you want to calculate. So for example, if I wanted the 50th term of my sequence, a recursive formula would not be very helpful because I'd have to generate all 49 that come before it before I could figure out what the 50th number is. So in that case, your explicit formula is much more helpful. But if we're just generating the first few terms, or we want one of the initial terms of a sequence, then a recursive formula isn't hard to work with. Our example here, what is the fourth term of the sequence that has a recursive formula? Again, they give you an initial condition, they tell us how to start, and then they tell us how to generate each term after that. So my first term is a 5. My second term, it says take the previous number, okay, a sub n minus 1, that is our previous answer, and then it says to add 2 to it. So I'm going to take my previous answer, add 2, it turns into a 7. To find the third term, I'm going to use the second term and add 2. To find the fourth term, I'm going to take the third term, which is a 9, add 2, and I get 11. So my fourth term of my sequence would be 11. So how do we come up with a recursive formula? The first thing to do is to identify that initial condition. What is the first term? It's going to be given to you. Then we look to see how each term compares to the previous term. And again, we're going to focus just on the 4 basic operations right now, adding, subtracting, multiplying, and dividing. So I would start out and say, okay, well, I know my first term is a 4. And then let's look at what are we doing each time. To go from 4 to a 7, we added 3. To go from a 7 to a 10, we added 3. To go from 10 to 13, we added 3. Same thing here. We're just going to keep adding 3. So I can say that to get any term of my sequence, a sub n, I'm going to take the previous term, so a subscript n minus 1, and I'm just going to add 3 to it. Those two parts both have to be present for your recursive formula. You have to have the initial condition, and then you have to have the formula that generates the next numbers. All right, let's look at another one. My first term here is a 3. Looking at what I'm going to do to go from 3 to 6, from 6 to 12, from 12 to 24. I'm just doubling everything. So I am multiplying by 2. So I would say my nth term will take the previous number and multiply it by 2. Again, I need both of those parts. So when the number we're adding, subtracting, multiplying, or dividing varies, which is not what we had in these two examples. In this one, we kept adding a 3. It was a constant number that we were adding. Here we kept multiplying by a 2. It didn't change from one term to the next. But if it does change, then we're not simply adding a constant. We're adding some variation, something that has to do with the n value. All right, so for this one, we start with a 1. To go from 1 to 5, I could add 4. To go from 5 to 14, I'm adding 9. To go from 14 to 30, I'm adding 16. To go from 30 to 55, I'm adding 25. And if you look at those numbers, 4, 9, 16, 25, those are all perfect square numbers. So what I'm doing, if my first term was a 1, my next term's a 5, 14, 30, 55. To go from the first term to the second term, I added 2 squared. To go from the second term to the third term, I added 9, which is 3 squared. So I'm just adding n squared to go from one term to the next. So my recursive formula, I would start out saying that my first term was a 1. My nth term is going to take the previous number and add to it n squared. All right, let's look at another one here. Our first term is 1, second term is 2, then 3, then 4, then 120, then 720. So my numbers are getting bigger quite quickly. And so let's think in terms of some multiplication. What am I doing to 1 to make it a 2? I'm multiplying by 2. To go from 2 to 6, I'm multiplying by 3. To go from 6 to 24, I am multiplying by 4. Now I'm multiplying by 5, 120 to 720, I'm multiplying by 6. So each time I'm multiplying by one extra number, and that just represents the position it's in. So here's my first term, second term, third term, fourth term, fifth term, sixth term. So I'm taking my first term of 1, and each term after that is going to take the previous term and multiply it by my n value, by its position. So to get the second term, I multiplied by a 2. To get the third term, I multiplied the previous number by a 3. To get my fourth term, I multiplied the previous number by 4, etc. Okay, so again, I need both parts to my recursive formula. All right, our last example here, it says the number of blocks in a two-dimensional pyramid is a sequence that follows a recursive formula. What is the recursive definition for this sequence? So let's start out looking at our position number. This is 1, 2, 3, 4, 5, and 6. Okay, so my first term just has 1 block. My second term has 3 blocks. So this is n, this would be a sub n, the number of blocks in the pyramid. My third picture has 6 blocks. My fourth picture has 10 blocks. Fifth picture has 15, and the sixth one has 21. So if you compare, I take the previous number, and in this case, I added 2. To go from that term to the next one, I take the previous amount, which was that section, and now I'm adding 3 more. To get to the next one, I take the previous part, that previous term, this time I'm adding 4. Here I'm taking everything I had from the previous picture, and I'm adding 5 to it. And then the same thing here, I take my previous picture, and now I'm adding 6 more. So that bottom row just keeps getting added that has 1 extra number in it. So my first term is a 1. My second term, or sorry, my nth term is going to be the previous number plus its n value, its position. So to get the third term, I take the previous number, add 3. To get to the fourth term, I take the previous number and add 4. So I'm just going to keep adding my n value to keep going. So I take the previous number, a sub n minus 1, and I'm just adding n to it. All right, so your goal today is to make sure you understand the definition of a sequence and what's the difference between a recursive and an explicit formula, when it's best to use each of those, and then just to get a few examples of creating an explicit or a recursive formula based on a sequence of numbers. Then tomorrow we will start looking at a specific type called arithmetic sequences.